Good evening, everyone. Welcome to CPA Presents. It's Monday, May 19th, 2025. My name is Mike Kaselniak, and I am the CPA Flight Safety Chair. Tonight's topic is for the CPA Presents is density altitude, estimating its effects, and we're going to have a demonstration of a software tool tonight. And this is presented by Mr. James Greer Jr., PhD, Lieutenant Colonel, United States Air Force, retired. Mr. Greer will discuss the effects of density altitude, some common methods for estimating its impact on performance, and an educational software tool he developed to compare some of these methods, including automating the venerable Koch Chart. Jim's most recent job was as a mechanical engineering professor at the Air Force Academy, where he was also the technical director of the Center for Aircraft Structural Life Extension. He spent nearly 40 years in and around the Air Force as a military officer, contractor, civilian employee. Jim earned his bachelor's degree in aerospace engineering from the University of Florida. His master's and PhD in aeronautical engineering are from the Air Force Institute of Technology. He holds a commercial pilot certificate with instrument and multi-engine ratings, as well as an advanced ground instructor and instrument ground instructor certificates. If you would like to receive Wings credit for this presentation, please email me at flightsafety@coloradopilots.org. Now, during tonight's presentation, if you have any questions, please put them in the chat. And at the end of the presentation, we will go through each of the questions that are in the chat. Okay. And if you have any questions, also put those into the chat for me, and I'll be monitoring and admitting people as we go along here. So now I would like to turn this over to Mr. Jim Greer. And Jim, thank you very much for accepting our invitation. And I am going to switch it over so you are the host. You will take over the host spot. Okay. And yes. Okay. As they say, you have the comm.
Okay, well, thanks very much, Mike. I'm going to see if I can share my screen and you can tell me if that worked.
Yep.
Okay. Well, thanks everybody for coming tonight. Really appreciate your attendance. I'm going to speak about density altitude tonight, as Mike said. I live in the Colorado Springs area near the Air Force Academy. I've been flying in Colorado since around 2003 or 4. And my home airport is Meadow Lake Airport in just east of Colorado Springs. So first I wanted to thank Mike and CPA for the invitation to present this information. And I wanted to thank the FAA's FAST team for inviting the broader aviation community. And of course, thanks to all of you who tuned in. I wanted to let you know that CPA nor FAA have reviewed my slides or this presentation, so any mistakes in here are all me. So an outline of the presentation, we're going to talk about what the definition of density altitude is, the effects of humidity on it, why we as pilots should care about density altitude, and then talk about some of the methods used to estimate or calculate density altitude, things like the Koch chart, but there are a lot of other tools people have used to estimate the effects of density altitude. And then at the end of the presentation, I'm going to demonstrate some software that compares the output of 4 different methods to estimate the effects of density altitude on both takeoff performance and rate of climb. So first, a quick review of the types of altitude that you learned when you were studying for your private pilot license. True altitude is your actual altitude above mean sea level. And if you're parked at the airport, it's going to be the airport elevation, provided, of course, that you're parked at the location where they measured the airport elevation. Where I fly, it slopes quite a bit from one end of the airport to the other. So your true altitude might not be airport elevation depending on where you're parked. The next altitude I want to talk about is if you correct true altitude for non-standard pressure, you can calculate your pressure altitude. The easy way to do this is to just set your altimeter to 2992 and read it, and that's your pressure altitude. But if you're not in an airplane with an altimeter, you can use this chart the FAA publishes in their Pilot's Handbook of Aeronautical Knowledge, and it'll give you the corrections to get pressure altitude from true altitude. Most of you probably know that the pressure altitude changes about 1,000 feet for each inch of mercury of altimeter setting. But what we're really interested in finding is the density altitude. And that's what you get when you correct the pressure altitude for non-standard temperature. And you've probably seen this chart before, but it's also in the Pilot's Handbook of Aeronautical Knowledge. You find your pressure altitude, and then there's this scale at the bottom of this chart of temperature. You find your temperature, your outside temperature, go up to the pressure altitude that you've calculated, and then over to the left axis of this chart and read your density altitude. Humidity also plays an effect, although this chart doesn't account for that. But humidity, higher humidity does make your density altitude higher. The Pilot's Handbook says there's no rule of thumb or chart for calculating the effective humidity, but that you need to take it into consideration. It says to expect a decrease in overall performance in high humidity. And while the Handbook of Aeronautical Knowledge says there's no rule of thumb for assessing humidity, there actually is. A couple of guys at Embry-Riddle Aeronautical University in Daytona Beach published a paper back in 2016 where they came up with a simple correction for humidity. Actually, it's 20 feet of altitude for every degree C of dew point temperature. So if you're at 20 degrees C dew point, then you'd add 400 feet to your density altitude. So you can see it's not a huge effect, but it's not insignificant. But most charts that you use, and if you use your E6B computer, you won't have a humidity correction in there. So this is a picture of the software I'm going to show you later tonight. But one of the features of the software is if you plug in a station ID and click Get METAR, you can get this bar chart of the altitudes: true altitude, pressure altitude, dry density altitude, which is density altitude before you correct for humidity, and then the red bar is your density altitude. And you can see in this case, this was from Meadow Lake Airport, and the humidity here was very low, 18%. And if you look up here to the right, you'll see that the effect of the humidity is only to add 47 feet to your density altitude. Not a huge difference. We can take this same scenario and crank up the dew point to get to 100% relative humidity, which you can see over here. And we can get the maximum effective humidity for these conditions on the density altitude. And we see here that the effective density altitude is to add 300 feet, or the effective humidity rather, is to add about 277 feet to our density altitude. Comparing the effects of temperature and humidity at a relatively high altitude airport like Denver, if you go from 60 degrees F to 80 degrees F, you're going to need to add about 1,350 feet to your density altitude. If you go from 10% to 90% humidity, that's only a 300-foot difference. So the reason I show this chart is just to show you that temperature is the big deal with density altitude, not humidity. And why do we care about density altitude? This again is from the Pilot's Handbook of Aeronautical Knowledge. Density altitude is the altitude the airplane thinks it's at in terms of performance. So regardless of your actual altitude, the aircraft is going to perform as though it were flying or trying to take off from the density altitude. And if you do a quick search online of density altitude related incidents and accidents, you'll find a lot of them. These are all cases where density altitude was cited as at least a contributing factor to the accident. Now with cameras and GoPros being everywhere, you can find films of some of these. The one in the upper right, the Bruce's Meadow crash, in which fortunately no one was killed, is a case where they were able to take off, but they just couldn't climb at their flight conditions. So how do you calculate density altitude? Well, in ground school, you learn how to calculate it on your E6B whiz wheel computer. Of course, there are electronic E6Bs too. I know Sporty's has one, and there are probably others. You can use a formula to estimate it. This formula shown here says to get density altitude, first find your pressure altitude, and then multiply 120 feet times the difference between your outside air temperature and the standard outside air temperature for your pressure altitude. So you can see if your outside air temperature is the same as your standard air temperature for your altitude, this whole term goes to zero, and your density altitude will equal your pressure altitude. Whereas if you have a difference in temperature, the higher your outside air temperature, for every degree centigrade higher, you're going to add 120 feet to your pressure altitude. You could also use paper charts. We looked at one that's in the Pilot's Handbook of Aeronautical Knowledge. You can use software like I'm going to show you in a few minutes, or you can just look at it in your electronic flight book if you have something like ForeFlight. If you plug in an airport into ForeFlight, and I assume this is true for other electronic flight books, although ForeFlight is what I have, it tells you the density altitude right on the screen there. Okay, so these are the things, and this isn't an exhaustive list, but these are the things that density altitude affects. Some of them for the better, but most of them for the worse. The higher density altitude, the worse your takeoff distance, the worse your propeller is performing, your engine power is lower. Flight pilot physiology, of course, if your density altitude's high enough, you can experience hypoxia, for example. But for the rest of this presentation, we're going to focus on two of density altitude's effects, and that's takeoff distance and rate of climb. And we'll start by looking at the Koch chart. The Koch chart is something you may have seen on the counter at your FBO. The FAA still cites it in this FAA pamphlet. It says if you don't have your flight manual or your POH, to use the Koch chart to calculate the approximate temperature and altitude adjustments for aircraft takeoff distance and rate of climb. And it's getting a little bit long in the tooth now. This is a 2008 publication, but it's still available on both the FAA and the NTSB's websites. This is what the Koch chart looks like. It's called a nomograph. It's got three vertical axes on it, as you can see. And the way it works is you plot your outdoor air temperature, your station temperature in degrees Fahrenheit on the left axis. You put a point at your pressure altitude on the right axis. And again, you find your pressure altitude at least most easily by setting your altimeter to 29.92. And you connect those 2 points with a straight line. And where it crosses the third axis of the nomograph, that gives you the information we're looking for. It tells you how much distance to add to your normal takeoff distance, and normal means at your current aircraft weight under standard temperature and pressure conditions at sea level. And it also calculates the decrease in your rate of climb. So in this particular case, it's telling us to add 200% to our takeoff distance and to decrease our rate of climb by 73%. So how did the Koch chart come up with these particular numbers? I'm not sure. What I've been able to dig up is the earliest Koch chart I found was in a 1950s Army helicopter flight manual. But another source I saw said it was developed in the 30s by Dr. Koch over in Germany. Here's where it first appeared, at least where I first saw it in FAA publications. Back in 1964-65, they published the Koch chart in this flight instructor exam guide, and it's hard to read. I'm going to zoom in on it. Maybe you'll be able to see here, but you'll notice the top of the Koch chart here says add 125% to your takeoff distance. That's different than today's Koch chart, and in fact, they rescinded this one, and in 1967 published a revised one. And that's the one that's available today. It goes up to 260% addition to your takeoff run and 90% decrease in your climb rate. This one came out, like I said, in around 67. And if you find a Koch chart today, that's the one you'll see. So somebody decided in the late 60s that Dr. Koch's correction factors weren't conservative enough. At the same time the FAA published that revision, they also came out with this whiz-wheel computer called the Denalt computer. And Denalt is a contraction for density altitude. This version, as you can read on the rim of the computer, is for variable pitch propellers, but they also issued one for fixed pitch propellers. And there's a new version out of this that's available today that I'll show you in a couple of slides. But this is another way to assess the effect of density altitude on your takeoff and rate of climb. And you can see up here is the pressure altitude window. Over here is the air temperature window. So you put your your air temperature in this window. You look along here for your pressure altitude, and it says, for example, multiply your takeoff distance by 2.7 in this case. So the Koch chart, it turns out, while it does show you what to add to your takeoff distance and percent decrease in rate of climb, my suspicion is it really started as a density altitude calculator. And let me show you what I mean by that. If we pick conditions that result in zero density altitude, like standard day sea level, and put that on our chart, and then find another condition that also results in a zero density altitude, for example, a cold day in Wichita, when we see where those lines cross, we can add a scale on here and call that zero. And we can do that for a bunch of conditions and see where we end up as far as a density altitude scale. And it turns out that if you, for example, here's Meadow Lake Airport on an 82-degree day with a certain altimeter setting, it gives you a 10,000 foot density altitude, and you can calculate that a number of ways, but I use the FAA's website, which has a density altitude calculator on it, and I'll put a link in the comments to where to get that or where to find that calculator. Let's find another place with a 10,000 foot density altitude. Here's a cool day in Lake County Airport in Leadville, Colorado, 27 degrees. Their airport elevation is almost 10,000 feet, the highest airport in North America, as far as I know. We can put another tick mark there and call that 10,000. And if you do this enough times, you figure out that this scale actually is a very linear, evenly spaced density altitude scale. So what this nomograph is doing in the background is calculating your density altitude, and what Dr. Koch did and what the FAA later revised was to try to put numbers on there that connect the density altitude to the effect on your takeoff distance and rate of climb. So These are the conditions I showed before for 10,000 foot density altitude. You can see the chart is telling us to add somewhere between 230 and 240% to our takeoff roll, and to decrease our rate of climb by something a little over 75%. And those numbers you can see here. Excuse me. What we can do is take those numbers off Koch's chart and plot them against density altitude, and we get a curve that looks like this. This is how much you're supposed to add to your takeoff distance for a given density altitude. But as I mentioned before, the Koch chart is not the only way people have estimated the effective density altitude. So let's look at 3 other methods that have been used to estimate the effective density altitude on takeoff and rate of climb. You may have heard of Sparky Imeson. He wrote a book called The Mountain Flying Bible, and in that book he has some rules of thumb for the impact of density altitude on your takeoff performance. This green line represents his rule of thumb, which is to add 12% to your takeoff roll for every 1,000 feet of density altitude. And then once you get past 8,000 feet of density altitude, you add 20% to your takeoff roll for every 1,000 feet. And that's why there's a bend in this line right here at 8,000. You can see it's not quite as conservative as the Koch chart would be. The Koch chart penalizes you more than the Imeson rule of thumb. And Imeson had rules for both fixed pitch propeller airplanes and variable pitch propeller airplanes. And I should say that this is all normally aspirated airplanes, not turbocharged airplanes. You'll notice that for a variable pitch propeller or a constant speed prop, the penalty's not as bad. That's because a variable pitch prop, obviously you can change the pitch to take a bigger bite out of the thinner air, and it doesn't suffer as much as a fixed pitch propeller airplane does from the increase in density altitude. This purple line is taking all the points off the Denalt computer that I showed you earlier and plotting a curve based on those points. This is what the more modern version of that computer looks like. It has scales for both variable pitch propellers and fixed pitch propeller airplanes on the same device. This one happened to be made in 1991 by a contractor in California. So at some point, the FAA handed this computer off to somebody else. And like with Imeson, Denalt has the variable pitch curve as well. And as you can see, once again, the variable pitch propeller airplane is not as badly affected as the fixed pitch propeller plane. And that the Denalt computer gives you more conservative effects than Imeson's rules of thumb, but less, except at lower altitudes, less than the Koch chart does. And finally, James Embree wrote a book in 1984 called Axioms of Flight. And in that book, he came up with a whole bunch of rules of thumb for many things beyond takeoff and rate of climb. But he does have rules of thumb in there for takeoff and rate of climb. And this orange line here is for the fixed pitch propeller airplanes, and this dotted line for variable pitch propeller airplanes. And you can see they kind of fall in the same neighborhood as the Denalt estimates do. So these are all rules of thumb and estimates. Let's compare them to some actual flight manual data. I'll throw on there some data from a Cessna 172 handbook. And if we isolate those points against the Imeson fixed pitch, because this is a fixed pitch propeller airplane, we see that it matches pretty well to the Imeson curve. We can throw on these magenta circles for the Piper Cherokee Warrior 2. And we see that they happen to match the Denalt and the Embree curves. It makes me wonder if maybe Piper, for the purposes of their manual, used an analytical solution rather than a flight test, because those points are just perfectly on that 15% slope line. And finally, let's add some data points from a variable pitch propeller airplane. These blue triangles are for the Cessna 182. And they match the Imeson variable pitch pretty well. And I suspect that most of these rules of thumb, the way they came up, these different authors and sources came up with them had a lot to do with the airplanes they were flying at the time, because they're all a little bit different, except for Denalt and the Embree fixed pitch curve. They don't fall on top of each other very well. But these are 4 of the tools that people have used to try to get a handle on the impact of increasing density altitude on your takeoff and rate of climb performance. We didn't talk much about rate of climb, and I'm not going to go into the same level of detail here, but I will show you what those curves look like. Here's how Koch says density altitude affects your rate of climb. At least I should probably caveat that and say it's Koch as revised by the FAA in the late 60s. Embree and Imeson both use the same rule of thumb for their effects for both fixed pitch and variable pitch propeller aircraft. Denalt follows the Embree and Imeson line until about 8,500 feet. And then if you plot all the points that are available on that flight computer, there's this kind of strange gap right here where these gray dotted lines are. And I guess the authors of that device decided that once you get above about 8,500 feet, you really need to take a bigger penalty on rate of climb. So it jumps down to something like the Koch curve here. And that's true for the variable pitch propeller case as well. You can see there's this jump here in the line as you pass through about 8,500 feet. So that's the effect of rate of density altitude on rate of climb by these 4 different sources. These are just both of those charts on the same page, and they're available in the software I'm about to show you. And I'm going to get to that next. But before I pull up the software, I would like to just give you a little preview of some of the things you're going to see in it that might be hard to see in the actual demo. The software is free, by the way, and you can download it from this site. I'll put a link in the comments. In fact, just to make sure I can do that.
Excuse me, Jim.
Yes.
We have somebody in the waiting room, and I thought I had access to let them in, but I guess I don't because you're the host now. Are you able to do that, or should I just reclaim host for a minute?
I think I need to, oh, I see it.
Sorry for the interruption, folks.
Oh, no problem.
I think I just learned something for next time.
Okay, I think I've admitted them. And Mike, I think I've unmuted you. Nope, I'm going to give you control back so you can unmute.
Okay. Okay, the gentleman is in, so it worked. Thank you.
Okay. But while I'm here, Mike, I'm going to go ahead and put those links in the comments. So did that show up okay? Can you see that all right, Mike?
Yep.
Okay.
Okay.
And
So for the participants, this session of this presentation, this whole presentation is being recorded, and we will edit it and we will put it online at the CPA website and on YouTube for the future. There's some questions about will the slides be accessible? We'll get to the questions at the end, but just so everybody out there is aware that this is being recorded for future viewing.
thanks, Mike.
You're welcome.
This link that I'm putting up now is for NOAA's online density altitude calculator.
Yep, it's
And
there.
bear with me while I put up one more. And that's the 2007 pamphlet the FAA published on density altitude that I showed at the beginning of the presentation.
Yeah.
Okay. So with that, Mike, if you want to send it back to me, I'll get back to my last couple of slides here.
Okay, let me see what we did. Oh, you're still the host.
Okay.
Yep. Yep, looks good.
Okay. Great. So I put those links up in the comments now. And before I get to the software, just a disclaimer, this software is not a flight planning tool, it's an educational tool so that you can see the effects of density altitude on takeoff distance and rate of climb. It doesn't fulfill the requirements of pre-flight action under FAR 91.103. And I guess I wanted to summarize or emphasize this in doing my research for this presentation. One thing I've seen is that a lot of these DA accidents are folks that have been able to take off but not climb. So you could use a Koch chart or any of these rules of thumb and add your 200% or 230% to your takeoff roll, and you say, well, I've got a 10,000 foot runway, I'm good. But you might find out you can't climb out of ground effect, and you can't get over surrounding terrain or trees at the end of the runway. And that is a common scenario that I see in these density altitude accidents, unfortunately. So this is what the software interface looks like, and it pops out a Koch chart really quick once you put in your airport identification. And these are this is a bar chart that it will show you. At the bottom of the bar chart is the rate of climb performance. At the very bottom, the blue bar is what you put in for your standard day sea level performance. And then the other colored bars are the rules of thumb and the Koch chart application based on the density altitude. So you can see in this case, a 700-foot rate of climb at sea level becomes 310 according to the Embree rules. The next set of bars is takeoff distance corrected for density altitude. So the blue bar, once again, is what you put in for your standard day sea level performance. And these other bars are the rules of thumb being applied to that 900 foot, in this case, takeoff distance. And then finally, the top set of bars is if you put in, it will apply corrections for wind, runway slope, and runway surface if you put in that information. So with that, I'm going to jump over to the software. So once you download the software, you'll have this icon in whatever folder you put the software in, and double click on it and you'll get that same disclaimer or something similar to that disclaimer we already discussed. And if you agree, you click accept and that launches the program. Now, just by way of introduction, this has a typical Windows file menu at the top. Um, the file menu includes recent stations you may have looked at with this program, of course, an exit button. There's a help menu, and the help menu has an about page, a check for updates button, because the software does get updated with new information occasionally and bug fixes. And then a link to that Koch Chart video on YouTube that I also put the link up in the comments. So the easiest way to use this software is first to put in your standard day sea level performance. By the way, blue windows in this software are inputs. Green windows in general are output from the program. So once you fill in blue windows, you get filled in green windows. Anyway, back to what I said would be the first thing to do. Your standard day sea level takeoff distance and your standard day sea level rate of climb. So I'm going to pretend I've got my POH here and it says on a standard day at sea level, and I'm going to fill my plane up to gross weight because even though it's a really hot day, because I'm not being very smart, and it says the takeoff distance is 1,000 feet. So I'll put 1,000 feet in here. It also says my standard day rate of climb is 750 feet per minute. Okay, now I'm ready to either manually fill in all these numbers up here, my altimeter, station elevation, temperature, and dew point, or I can just go up here to station ID, put in my airport, I'll put in KFLY, and click Get METAR. And it goes out and retrieves the METAR for Meadow Lake. It fills in all the information I need, altimeter, station elevation, temperature, and dew point. And I can go down here and I can plot a Koch chart just by clicking on the Koch chart button. And you can see at the top of the chart, it tells me what airport this is for, when this, it just repeats the METAR at the top here, because you could also get another nearby airport, say the Air Force Academy, and plot that Koch chart. And you would know which Koch chart is which by the heading at the top of the Koch chart. And you'll also notice that down at the bottom of the page here, we have calculated now our pressure altitude based on the altimeter, our relative humidity based on temperature and dew point, our density altitude, which is based on pressure, altitude, temperature, and humidity. And then since we put in our standard day performance, it tells us our new Koch takeoff distance and our new Koch rate of climb. And we can see that in bar graph form if we click this button, Show Takeoff Bar Graph. And the blue bars are our sea level performance. The red bars are the Koch numbers based on the Koch chart. If we didn't put in our standard day sea level numbers, we wouldn't get the red bars because it doesn't know what to multiply those factors by. The other thing you could do, if you just like to look at what your different altitudes are, you can click altitude chart and it will show you your true altitude, which is just your station elevation. It will correct that for pressure and give you your pressure altitude. In this case, you can see the pressure altitude's higher than true altitude because the altimeter setting is less than 29.92, which is standard altitude or altimeter setting. It gives you your dry density altitude, in this case 7388, which does not account for humidity. And given our 76% humidity right now, it gives us our actual density altitude, which is 7,510 feet. So the humidity is changing our density altitude by 130 feet or so. Not much. So that's what the Koch chart tab will do for you. The next tab I'd like to show you is the Imeson tab. We can get the Imeson takeoff distance and the Imeson rate of climb just by touching this calculate button here. But we need to decide if we want the fixed pitch number or the variable pitch numbers. And that, of course, would depend on your airplane. I'm going to choose variable pitch propeller and click calculate. So now I have the Imeson takeoff distance and the Imeson rate of climb. It says Embree / Imeson because if you recall, they both use the same rule of thumb. And if I click on my show takeoff bar graph, now I have these green bars, which are for Imeson. They've been added to the bar graph. Excuse me. I mentioned that you can correct these numbers for wind, for runway slope, and for runway surface. So let's go ahead and do that now. I am going to go back to my Koch tab and change my airport back to K-Fly. And then go back to my Imeson chart, recalculate my Imeson numbers. And now let's correct for these different things I talked about: wind, slope, and surface. There is at the bottom of this page a wind calculator. So it allows you to calculate your headwind component very quickly based on the information from the METAR, which is reproduced at the bottom of the page down here. Notice that our wind is from 280 at 6 knots, which is true. I don't mean that's true. I mean it's true heading, true course actually. Given our variation, which the program has automatically pulled up from an FAA database of 7 degrees east, that gives us our magnetic winds of 273 at 6. And then we can pick a runway to use and it'll calculate the wind components. Now, if we don't know what runways KFLY has, we can just click this button, show runway info, and it will pop up a window with the different runways. Given that the winds are from 273, let's see, I'll choose runway 33, put 33 in here and hit enter. And you can see I have a headwind component of 3.3 knots. And that automatically gets populated up here in our correction box. And it automatically selects this radio button for headwind. The only other thing we need to correct for the effects of our headwind is our rotation speed, because the Imeson needs that to factor in the headwind. I'm going to say I'm flying my 172, then my rotation speed is 55 knots. So I'll put that in there. I happen to know that the runway slope for runway 33 is uphill, and it's 1.4 degrees. So I'll put that in here. The uphill radio button is clicked. And then I have to choose my runway surface. Runway 33 is a hard surface runway. But just to show you that the different corrections it can do, I'm going to change it to firm turf. So now we've corrected for wind, slope, and runway surface. And we click calculate, and we get our new Imeson numbers. Our new Imeson takeoff distance is here. Our new Koch takeoff distance is here because the program has applied these Imeson corrections to our Koch takeoff distance. If we look at our bar graph, now we have these bars up here for the corrected values based on wind, based not only on density altitude, but also wind, slope, and runway surface. And really, we've done everything hard that you have to do in the program. because the most time consuming part is the wind, slope, and surface, if you even want to correct for those. Now we can look at the Denalt and Embree corrections, but they use the numbers we've already put in, so there's no more calculating to be done. If we click on the Denalt tab, it takes us to this tab, and you can see everything's filled in. And if we click on our bar graph, you can see now we have these purple bars for rate of climb and takeoff distance, and those are from the Denalt computer. Similarly, we can go to the Embree tab. We find that that's fully populated with all the information we already put in. We can pull up our bar graph, and now we have the orange bars added. So we've got, for the 4 methods we've discussed in this presentation, we've got our estimated takeoff distance and rate of climb. And the header on this chart tells us that this is for Meadow Lake Airport on this date and time. The last tab is the Compare tab. That just takes those charts we were looking at earlier and draws a red vertical line at our particular density altitude. And that's from the Koch tab. The first thing we did was calculate density altitude, and we see that that's 7,700 feet. And the purpose of this chart is just to show you where the different estimation techniques fall for our particular conditions right now at 7,700 density altitude. This line moves depending on what you did on the very first tab. And that is the software. You're welcome to download it, play with it. There's an email address on there to send me your comments or bug reports. I'll get back to you as soon as I can on those. If you know anybody else that's not with us tonight that might be interested in it, share the link with them. There's no charge for this software. And let's see, I'm going to switch back to my slides. I think I have 2 slides left. Just for some closing comments. So unless your performance charts take non-standard pressure and temperature into account, you always need to calculate a density altitude because your aircraft will perform based on that altitude, not field elevation. And I know I've foot stomped this already, but at high density altitudes, you may be able to take off yet not be able to climb. So just because you can calculate a takeoff distance, don't assume you're good. Pay special attention to weight, reduce it when you can, and leaning. So in some cases, you might even want to do a full power run up in a place with no rocks on the tarmac, because you want to get maximum power on your takeoff. And Mike, with that, I will turn control back over to you.
Okay. Let me get in here. We do have some questions, and we'll get to those, and then we'll open it up. We'll open the floor up to the folks. Okay. Now, okay, let me get in here. All right. Reclaim host. Okay, very good. All right, now get in back into the chat. Okay, let me open this up. Whoops. Okay. No. Okay. When you were talking about the dew point, someone said 20 feet per dew point. Wow. Any way we could get a link to that paper?
Absolutely. Yes, I will. Well, as you give me the next question, I'll look that up right quick.
Okay. This one was asked by an individual and answered by one of our attendees, but I thought it was pretty good. When you were talking about the Koch chart, what if the result is off the chart? E.g., if it's 90 degrees in Leadville, what do you do?
That's a great question. If you will find that if you put in, say, Boston on a cold day or Leadville on a hot day, the windows will not, the software will give you an answer that says off chart. It will not attempt to extrapolate outside the chart. So in that case, you're pretty much out of luck.
Yeah.
Thanks
One of
for that
the
question. That's an important one.
yeah, one of the attendees says, "Go have a cold beverage instead of flying."
Yes.
Another question was, does some of that have to do with the wing type, the wing style of the airplane? I'm not sure on the Koch chart what they mean.
I don't know the answer to that.
Okay.
I assume that the question has to do with if you have a thick wing like a Warrior or a laminar flow wing like a Mooney, how does density altitude play into those things? And I don't have an answer for you for that.
Okay. All right. Are the slides accessible? And we said that they would be on the video. Is there a link for Apple or Mac products to run the software?
I do not have a Apple or iOS version of this software available.
Okay.
I saw somebody answered that question though with something about parallels. Maybe
Yeah,
that's
I
a
see
piece of
that as
software.
well. Yeah. Okay. And one of the questions, ever thought about putting this into a web app or releasing an app that could be used on your phone?
Yes, I have. In fact, the Koch Chart software started as an iPhone app, uh, but due to hardware issues or hardware accessibility issues I had, and the fact that the program became much more than just the Koch Chart, I don't have an iOS version of this software. I'm debating whether or not I'm going to try to tackle that.
Okay. Another question was, so on the chart, he had a 172 and a 182, which were close. Then the Piper had worse performance. That's probably back to the wing question because it's the same uh, person that asked about the wing configuration.
Yeah, those were just examples. I don't know. I think the 172 was a 160 horse version, a 1978 version of that airplane. I don't remember the horsepower of the Warrior, which had like the questioner said, had worse performance. But those were just some examples I grabbed off my bookshelf because those are airplanes I had the POH for. Uh, so it could be that the Warrior has less horsepower than the 172 or just poorer performance for takeoff. I don't know the answer.
Okay. All righty. All right. Those were all the questions in the chat. I'm going to open the floor up to anybody that's watching. If you want to unmute yourself and ask some questions, please go right ahead. Anybody out there with any questions? We got some more people that are okay. All right. Is anybody having trouble unmuting or can you unmute? I just want to make sure I'm not doing anything that's blocking you from unmuting. Okay. Adrian, I see that you're out there. Can you try to unmute and just so I know that it's working, please? Let me try this. All right. Oh, and I got something in the chat here.
Oh,
Okay.
I just posted the link
Oh,
to that
there he is.
paper.
Yeah.
Okay. All right. So it is.
Uh,
I'm not doing anything that I'm not supposed to be doing. This is my first night being the MC. Generally, our webmaster is. So, but he did leave me some great directions.
I was not able to unmute myself for some reason until
Oh,
you muted me.
oh, okay. Let me think. Allow, ask call to unmute and mute participants on entry, enable waiting room. Allow participants to unmute themselves. Okay. Now it should work. Yep, here we go. People are unmuting. Okay. Thanks for that tip, Adrian. I just found out where you were what you were talking about. There's that little menu that pops up. Okay. All right, and I'm going to get rid of that one. All right. All right. Okay.
Can I address Jason's question there?
Which one was that?
It's the last one, the most recent one.
Oh, okay. Yeah, go ahead.
Yeah, none of these tools try to the best of my knowledge, try to incorporate a turbocharged engine. So these tools only apply to normally aspirated engines, and that's a good observation that he makes, that the propeller and wings aren't turbocharged. Density altitude is definitely going to affect those, whether your engine's producing full horsepower or not. But none of these charts or tables take that into account. Stick to the POH.
Okay, good. Excuse me. I did some research today when I was reviewing everything, and I was like, I think you had mentioned it earlier too, that I couldn't find out who the originator of the Koch chart was. I didn't even come across anything that, like you said, when you found it in a Army manual for a 1950s type helicopter. I also looked up the Denalt, and the only thing I came across was a Philip Dalton and a PVH Weems, and they were both naval aviators in the 1930s, 1940s. But it didn't say that they were inventors of the Denalt. It said that they were the ones that pretty much, and it didn't say they knew each other either, but had to do with flight computers. And so these guys were working on those back in the 30s and the 40s, but it did not give them the credit for the Denalt. Sparky Imeson, as you mentioned, I have his book as well. I picked that up years ago, followed him along until his untimely death in 2009. But both his books are great books to read. It's pretty good. I did try to find out who the Embree person was. Had no luck there. So that was interesting. Um, Jim, if you could just touch on for the audience the difference between fixed pitch propeller and variable pitch.
Yeah, in a variable pitch propeller equipped airplane, or also called a constant speed prop airplane, you you'll have a manifold pressure gauge and a RPM gauge in your cockpit, and you've got a blue knob usually that you can use to set the RPMs. And as you adjust power or as conditions change, the pitch of the propeller and the angle of attack it creates with the relative wind will change to maintain a constant speed. So if you're flying into conditions where there's, um, I don't think I want to say it that way. I think I'll leave it with what I said. The propeller has a governor on it that will try to maintain a constant RPM.
Okay.
And in thinner air, that's helpful to you, because if you have a relatively flat fixed pitch propeller, it just does what it can do, and it can't increase its angle of attack to try to bite more out of the air and give you more performance.
Mm-hmm. Now, one of the last charts that you showed us, the bar chart, it had all four corrections for the different for the Koch chart, the Denalt, the Imeson, and the Embree. You have all that data sitting in front of you. Would you be conservative and go with the average, or would you be ultra conservative and go with the one that tells you to use the most landing room? I mean, how would you look at that with all the data?
Yeah, that's one of the reasons I refer to it as an educational tool, because it allows you to compare the different methods. As to which one's best, uh, I couldn't tell you. I'm sure if you took data for your own airplane and compared it to these rules of thumb, you'd find that one works best for you. That's a great question. I thought about that one a lot. Uh, I think it would be foolhardy just to take an average, for example. Uh, Obviously, it'd be conservative to just pick the longest one or the worst climb performance. But even that may not capture the performance of your particular airplane.
Okay, no, I agree. I agree with you 100% there. Okay, I when you first introduced this uh, presentation in the software, I think 2 months ago or whatever, when we first talked about it, I was amazed at how versatile it was and what it did. Uh, what was your drive to do this? What was behind it all to get you into this kind of depth of work? It's amazing.
Oh, well, thanks, Mike. I think one of the key events was in May of 2003, I retired. So I had some time. And as I started looking at density altitude and the Koch chart in particular, uh, that led me to start reading on density altitude. And then I found, of course, I had Imeson's book for a while, and I wanted to compare his rules to Koch and found they were different. So then I just started looking around for some other rules. And I think what really impacted me first and most was how drastic the effect is of density altitude on takeoff performance. It really, it's really a penalty. And those that have flown at high density altitudes, uh, as we were talking before we came on, most people have a story. I remember talking to a pilot up in a little airport in the Denver area that ended up flying around the pattern at 200 feet AGL because his airplane just wouldn't climb. He got it back on the ground, but learned a scary lesson about density altitude that day.
Yeah. Well, I just want to, all the attendees out there, the Colorado Pilots Association puts on a fantastic course in mountain flying. We offer, I believe, this year we're doing three courses here in Colorado, and we're doing one at Oshkosh. And people from not just Colorado, but all around the United States and foreign countries come to Colorado to take our courses. So I think Colorado Pilots Association does a good job of getting that out there for density altitude. And like I said earlier, this is a very good time to visit this since we're having the summer weather coming in the hot temperatures. So it's very good to put that back in our mindset for everybody that's out there. Again, if anybody's out there has a question, please chime in. I appreciate it.
This is Adrian. Just wanted to clarify one thing that the course that we do at Oshkosh is just a 1 hour, very brief overview of why it's important to do a mountain flying course. It's not a real complete course, and the courses we do here in Colorado are all a full day.
Okay, thank you, Adrian. Anybody else out there with any questions? I don't want to control the whole situation here, but I think it was a great presentation, and download that software and play with it. I mean, it's amazing, amazing stuff. All right.
Thank you, Mike.
All right. So you said you fly out of Meadow Lake. So that's, yeah. Okay, I've been down there a few times. Okay. All righty. If we have nobody else, well, wait a minute. Some more came on the chat. I've taken the CPA mountain flying course. Very informative. Learning just how ignorant I am about mountain flying. Spectacular presentation. Thank you. Thank you. Great presentation. Thank you for the great presentation. Thank you. Okay. Very good. All right. Again, Jim, thank you very much for accepting our invitation. I appreciate it.
It was my pleasure. Thank you.
And to everybody out there, thank you for joining us. I appreciate the attendees and the people coming to visit us on Mondays. All right. Adrian, is there anything else that you would like to say, sir?
No, I second the thanks to Jim for doing this. Very good.
Okay. In case the folks out there don't know it, Adrian Nye is the president of the Colorado Pilots Association. All right. Very good. All right. Again, thank you, Jim. Take care. Hope to see you around the airfields.
Thanks, Mike.